Well, welcome back and welcome to Philip. Thank you.
Okay, thank you very much. So good evening, everybody, and thank you for the invitation to speak. As I'm sure you've realized, I'm a particle physicist, not an astronomer. The reason that I offered to give this talk to GAS is that shortly after I joined a few months ago, there's an excellent talk on cosmology in which neutrinos featured significantly. So it's actually been several years since I've worked in neutrino physics, but it still occurred to me that members may be interested in hearing a little more about these fascinating little particles, what they are and how we investigate them. So without further ado, let's get started. If I go one slide at a time, there we go. So why are they interesting? They can tell us a lot about the universe. Potentially, they might address a very long-standing cosmological mystery about the matter-antimatter asymmetry in the universe, why the universe is dominated by matter, whereas at the time of the Big Bang, there should have been just as much antimatter produced as matter. In principle, it should all have annihilated and we should be left with an empty universe, but the laws of nature ended up with a little bit of matter left over for reasons that we don't quite understand. They can tell us about physics beyond our current standard model, which is certainly interesting to those of us in the particle physics field, and perhaps of more interest to astronomers, the cosmological evolution of the universe can be affected by neutrinos. Now, the measurement of neutrino properties is performed in very large scale experiments, and we'll see in due course why they have to be very large experiments on the whole. There are several different ways of detecting neutrinos, and each has their own benefits. And we'll have a look at what are the big questions in neutrino physics at the moment and how can we explore them. But let's start off by asking, what are they? I'll tell you, first of all, what they're not. They're not a constituent of atoms. So when you think of the sort of fundamental particles that we're very familiar with, within the atom, there's the tiny little nucleus in the middle, consisting of the protons and neutrons that are themselves made of quarks. And orbiting around the atom are the electrons. So this little diagram on the right here is way out of scale. The nucleus is tiny. If you imagine the nucleus as being about the size of the fist of my hand, then the outer electrons in an atom would be about 5 miles away. So the atom is actually mostly empty space. The neutrino, though, as I said, is not a constituent of atoms at all. It stands on its own. We use the symbol nu, which is a Greek letter. They're amongst the lightest of elementary particles. They travel at very nearly the speed of light all the time, and they very rarely interact with any other matter, and they can happily zip straight through the Earth. In fact, on average, it would take something like half a light year of lead to stop a typical neutrino. Now, the big difference that makes this happen is that all the other particles that make up matter carry electric charge. So electrons and protons can sort of interact with each other electrically. Neutrons have no electric charge, but they're bound in to the nuclei with the protons, and they have charges internally. But neutrinos have no electric charge at all. So the atom they just see as mostly empty space. They're tiny. They weigh in at around a 10 millionth of an electron. We don't yet know precisely how massive they are, but they're difficult critters to pin down. But although they're so tiny, their mass is so minute, there are many, many of them. And for every electron, proton, and neutron in the universe, there are roughly 1 billion neutrinos. So what this graph is showing, you see on the scale on the left, the number per cubic centimeter, and it's a logarithmic scale showing this factor of 1 billion neutrinos per electron and per proton. And this means there are something like 100 trillion passing through each of us every second. That's a lot of zeros. Those are American trillions, by the way. So where do neutrinos come from? Well, all of the neutrinos that are out there are a result of interactions of the weak nuclear force. So we'll look at some examples of neutrino sources. First and foremost, I have this annoying thing on my screen that I don't think I can do anything about, actually. It's blocking up part of my screen, the control bit at the top. Anyway, solar neutrinos, most of the neutrinos that pass through us actually come from the sun. This beautiful image of the sun is captured with ultraviolet light, and incidentally, you can see Venus transiting across the surface there. So this is the sun seen with ultraviolet light, but we can compare it with an image of the sun captured using neutrinos. This is a telescope image with telescope being 2 kilometers underground. So those are neutrinos from the sun showing up, neutrinos that the detector sees as having come from the direction of the sun. Now the sun shines because of nuclear fusion going on in its core. It's a sort of atom building process. Lighter atomic nuclei merge into heavier ones, and as part of this process, light is produced and neutrinos also come out, and we'll say more about that in due course. There are plenty of neutrinos left around from the Big Bang. There are roughly 30 million neutrinos from the Big Bang inside you right now. Of course, there's different 30 million at any given moment from the instance before. Radioactive decay is really a primary source. So the sun, you get the atom building, producing neutrinos, but the opposite of that is radioactive decay produces neutrinos. Now, here you see, as an example, a neutron, a free neutron, decaying into a proton, and I've shown the quarks here. You've got the neutron has got 2 down quarks and an up quark, and one of the down quarks turns into an up quark, turning the neutron into a proton, and as a result of that, it spits out a little particle called a W, which then decays into an electron antineutrino. So it's neutron decay, but it's similar with all radioactive decay processes. Yeah, radioactive, I should say, similar to all radioactive beta decay processes, always accompanied by the release of a neutrino or antineutrino. Now, this is an interesting source, geoneutrinos. It's really in its infancy, but radioactivity is actually what keeps the Earth's core molten. It's vital for our magnetic field that the Earth's core should be molten, moving around and acting like a dynamo. And radioactive decay actually also provides all of the helium supplies that we have. It all comes out of the ground from where it's trapped in oil wells. So party balloons, MRI scanners. I think my kids will probably be quite upset that when they get old and discover that they can't have MRI scans because all the world's helium is sent up in party balloons, but never mind that. So studying the neutrinos that come out from the Earth in principle can tell us about things going on in Earth's interior, but as I say, that really is early days for studying those. Exploding stars, something close to the heart of this audience, I know. So supernova explosions produce neutrinos. Famously, the supernova SN 1987A, the neutrinos, 11 neutrinos from that were actually detected on Earth. So supernova explosions, as I say, they produce neutrinos along with heavy chemical elements such as zinc and selenium and others. Then we have yet another source of neutrinos, atmospheric neutrinos. So here you have collisions between high energy cosmic rays with atoms high in the atmosphere, and they produce showers of particles, amongst which are many neutrinos that come down and strike the Earth. And here you see a sort of diagram of it. This is a very old diagram. I see it's Aleph in the bottom, which was a detector that predated the LHC. Anyway, so you have cosmic rays coming in at the top and then shower of particles coming down, lots of pions, and these decay, and you see gammas and electrons and all sorts of things. Muons live a long time, and some of those reach the surface, but neutrinos, when they're produced through the decays of the particles like the pions, the neutrinos would just go straight on, and most of them straight on down through the Earth. There are also man-made neutrinos. So the two pictures here on the left, you see Fermilab near Chicago. This is an accelerator, and so there are a couple of accelerator rings there, and then a straight stretch off in the top left, linear accelerator there. And so you can smash protons into targets, and the spray of particles that come out can produce beams of neutrinos. And on the right-hand side, you see the reactor at Bougie. Nuclear reactors also produce neutrinos. Bougie in France, there's a little peninsula that sticks out from France into Belgium. And that reactor is there. Now, neutrinos don't interact very much with anything. On average, as I think I said before, neutrinos could travel through something approaching a light year of lead before interacting. There's this nice quote from Douglas Adams about neutrinos traveling through Earth. The chances of a neutrino actually hitting something as it travels through all this howling emptiness are roughly comparable to that of dropping a ball bearing at random from a cruising 747 and hitting, say, an egg sandwich. Now, just for fun, a colleague of mine some years ago looked up flight paths and thought about, well, on average, how many people are sitting under a flight path eating an egg sandwich on a summer's day, and decided that actually that estimate is probably not far off. So if they interact so rarely, how can we see them, and how do we know that they should be there at all? There we go. So going back to the beginning, in the 1920s, there was a puzzle in the new quantum physics that was emerging. Study of radioactive beta decay seemed to indicate that energy was disappearing. Not just energy, actually, it also looked like a violation of angular momentum. And in radioactive decay processes, they added up the energies of the particles before and after, and there was a gap. And there was a famous conference. Wolfgang Pauli wasn't able to attend, but he sent his graduate student along with a letter. Dear radioactive ladies and gentlemen, I've hit upon a desperate remedy to save the law of conservation of energy. And his proposal was that there exists a tiny particle that is invisible, very difficult to detect, impossible to detect, that's carrying away the excess energy and angular momentum. And he wrote in his journal, I've done something very bad today by proposing a particle that cannot be detected. It's something no theorist should ever do. Perhaps tell that to the string theorists. But anyway, 1933, Enrico, oh, by the way, this neutrino was, the original proposal was that it should be called a neutron, but around the same time, I think 1932, what we now call the neutron was detected, and so it was decided to call the neutrino instead, which is a diminutive term. So 1933, Fermi formulated a really comprehensive theory of radioactive decays, and the neutrino was really crucial to the theory, and it worked out, was consistent with all measurements and so on. So the neutrino became an established part of particle physics, and its name, as it says there, means the little neutral one. But Pauli was convinced it could never be detected. But then 1956, Fred Reines and Clyde Cowan ran an experiment to detect the neutrinos. And they did this by putting some scintillators very, very close to a nuclear reactor and looking for what's called inverse beta decay. So you see this equation that I've put on the right there. I don't know whether you can see my mouse, but this is anti-neutrino, anti-electron neutrino from the reactor will hit a proton, and turn it into a neutron plus a positron. So it's like neutron decay, but the other way around. If you put the electron to the other side of that equation and flip it around, you can see it's like neutron decay, but backwards. So it's inverse neutron decay. And when that happens, the positron there gives a very specific signature because it annihilates from an electron, and you get two gamma rays coming out in opposite directions with a very specific energy. Anyway, they found these neutrinos. As an aside here, their first proposal was, rather than doing this next to a nuclear reactor, their first proposal was that a nuclear bomb should be set off. But fortunately, that was vetoed, and it was pointed out to them that a reactor is better because you get more than one chance at your experiment. It's lower level of neutrinos, but a continuous flux. Anyway, Pauli sent congratulations, and you see the congratulations note there on the right, along with the crate of champagne. And Reines, who was still alive in 1995, won the Nobel Prize for that work. Now, neutrino mass. It was long thought, I'm not sure that I should say it was long thought, it was long assumed, it was built into the standard model, the assumption that neutrinos weigh precisely nothing, just makes the maths easier. It's not as strange as it sounds. Photons, which are basically particles of light, have got zero mass. However, it was demonstrated in 1998, and we'll come to that in a while, that neutrinos do actually weigh something. Mass is tiny, and as I mentioned earlier, it's at most a millionth, or more like a 10 millionth of the mass of the electron, which itself I've written in kilograms there with yeah, lots of zeros. But the total mass of neutrinos, excuse me, is probably of the same order as the mass of all the other ordinary matter in the universe, which is why they have to be considered when you're considering cosmic evolution. Now, in the search to measure neutrino mass, you need large detectors. This is the KATRIN experiment, and it's a very, very sensitive spectrometer. Basically, like the old cathode ray tubes. So you would have your source at one end of it. You imagine the old television set that would give out electrons from a heated cathode and use magnetic fields to bend the electrons to hit the screen in just the right place. In this spectrometer, there's a tritium source, and when there's a radioactive decay, then the electron comes out, and magnetic fields are used to bend the electrons to different channels in a detector according to their energy. So you can measure the energy spectrum of the electrons coming out. And you see the kind of spectrum you get in this graph here on the right, energy on the horizontal axis and the number of electrons with that energy on the vertical axis. And the enlargement there in the middle is what you would see at the very tippy tail end of that spectrum in the green and in the blue is what you would get if the neutrino has zero mass, and the red is the deviation that you expect to that end if it's as much as 1 electron volt, whereas the electron is 500,000 electron volts. Now this spectrometer, because it's got to be so very sensitive, it's a huge, huge device, as you see, and it was built, I'm sorry, I've got in my notes, but I can't see my notes here. I can't remember the name of the place, Deggendorf in Germany, and it had to travel 350 kilometers to the place where it was going to be operated, the laboratory there, Karlsruhe. But the roads were too small. It couldn't fit on the motorways, wouldn't go under the bridges and so on. And they worked out that by taking it, instead of 350 kilometers, they could take it 9,000 kilometers through this circuitous route, mainly by sea all around and back close to where it started. And you see the picture on the top left, actually what limited the size of the spectrometer was the space between this pair of houses there, as the spectrometer was nearing its final destination. And the latest result was actually earlier this year, was that the mass is less than 800 milli-electron volts. So that's 0.8 electron volts. So if you compare with the graph below, 1 electron volt is the difference between the red and the blue, and they found that it's less than 0.8 electron volts, but still some way to go. Cosmological models limit it to perhaps you know, not quite factor of 10, less than that. So neutrino detectors, let me go on to talk briefly about those. Key point is that neutrino detectors have to be massive, really, really massive. Neutrinos hardly ever interact. As I said, they can pass, most of them can pass readily through the Earth. So chances of them hitting a target atom in the detector are very small. So you need lots and lots and lots of those target atoms within the detector to catch any of the neutrinos that go through. So for example, I talked about all the gazillions of neutrinos that are going through your body all the time. But despite that, only probably 2 or 3 will interact within your body in your lifetime. So they won't do you any harm. So as well as having lots of target atoms, you also need lots of neutrinos. You need a very intense source. Just as an aside there, you can only really see the results of the interactions, i.e., so if you've got a detector and you've got an electron going through it or a muon going through it or whatever, if a charged particle, you can directly see the track when these things are going through and disturbing the atoms and knocking electrons off the atoms that they go through. But with the neutrino, you don't see that at all. You only see the disturbance caused after they've hit a nucleus or an electron. You see the sort of rebound effect on the nucleus or the electron. You don't see the neutrinos themselves. So here are examples of neutrino detectors, and we will come back to these, but I'm just showing you them now just to give you a sense of the huge, the awesome scale of these machines. On the top left is Super-Kamiokande, which is about 50,000 tons of very pure water with a lot of photomultiplier tubes. We have the Nova detector, top right, huge, huge sheets of scintillators. The Sudbury Neutrino Observatory, bottom left, that's only 12 meters across, contains heavy water. And MINOS on the bottom right, 5,000 tons of steel and plastic. That's the experiment that I worked on. I used to lead the neutrino physics group at Sussex, and that was a project I worked on at the time. Now, I'd like to talk to you, if I may, about neutrino oscillations. I know this is not a technical talk. It won't be too technical, but it's a little bit of quantum weirdness. I put these 3 images at the bottom there, well-known pictures that you can see in 2 different ways. So if you look at the one on the left, for example, you could interpret it as a vase, a yellow vase, or else the yellow in background and in black you see 2 silhouette faces. In the middle you can interpret that either as a rabbit looking to the right with its ears going to the left, or perhaps as a duck's head with the head on the right and the duck's bill on the left. Or the rightmost picture is a young woman looking away from you, and you can just catch the sort of profile of her nose and her hair flowing down, or you can see it as an old woman. The eye there, what's the ear of the young woman becomes the eye of the old woman, and the young woman's necklace becomes the old woman's mouth smiling, and so on. So the point here is that same thing can be interpreted in different ways, and neutrinos do something very similar. This is a sort of analogy. Now, neutrinos, when they're produced in these interactions that I talked about, the weak interaction like radioactive decay, and they're produced in three, what we call flavors. I know I've drawn them as lemon, strawberry, and lime, but they're really not. Flavors is just the physicist's name for the electron, muon, and tau type neutrinos. So when you have radioactive decay, the beta decay I talked about, you get an electron and an electron type neutrino. And if you have an interaction involving a muon, you always have a muon neutrino with it, and an interaction involving a tau, you get a tau neutrino with it. But these three types of neutrinos seem to have an identity crisis. Neutrinos have all got mass. There are three different neutrino masses that we call M1, M2, and M3. So you would naturally expect, excuse me, I just need to close this window. You'd naturally expect that the electron neutrino would have mass M1, muon neutrino would have mass M2, and the tau neutrino would have mass M3. Right? Makes sense. Life isn't that simple. The electron neutrino is sort of a mixture of the neutrino that's got mass M1 and a little bit of the neutrino that's got mass M2 and a tiny bit of the neutrino that's got mass M3. Very odd behavior. And the muon neutrino has got a different admixture, and the tau neutrino different again, the tau neutrino being mostly M3. How does this all work? You can picture this in different ways. I've drawn them on the top right there. Neutrino 1, neutrino 2, neutrino 3, having different mixtures of electron, muon, and tau neutrino. Or you can think of coordinate axes, if you like. Sorry, this image is very fuzzy, but I've drawn axes at right angles to each other, like X, Y, and Z axes, with neutrino 1 to the right, and neutrino 2 upwards, and neutrino 3 sort of towards us. And an interacting neutrino, an electron neutrino, for example, the red one, you can think of as a bit of neutrino 1, a bit of neutrino 2, a bit of neutrino 3, like that. It's a strange behavior, but this is the way that nature is, and we can't second guess it. As an example, you have the long-standing mystery of solar neutrinos. So neutrinos are produced in the sun in copious quantities, produced in the sun as electron neutrinos through the reaction you see here. A couple of hydrogen nuclei, or protons, in other words, on the left, smash together and they fuse. And out of that, you get a deuterium, which is a proton and a neutron, but also a positron, an anti-electron, that is, and a neutrino comes out. And so on, these other processes building up, you get helium-3 and then helium-4 and so on. But the point is that you get neutrinos coming out of these reactions, as well as gamma rays that bounce around and end up coming out of the sun as light and other electromagnetic radiation. Oh, got a little circle around my neutrino. But although the neutrinos are produced by this weak interaction with the specific flavor, it's electron neutrinos, as they move through space, when they're just traveling in space, they don't care about electron, mu, or tau. They care about mass, mass 1, mass 2, or mass 3. And for a given energy, the different neutrino masses will move in a slightly different speed, essentially. And so the mixture, it gets all jumbled up and out of phase. And so these neutrinos, when they start as electron neutrinos in the sun, by the time they get to Earth, they lose track of who they are. And there's a chance that they could be anything. They get to Earth and they interact in a detector, they hit a detector, but by the time they hit that detector, they don't know whether they're electron or muon or tau anymore. They've sort of lost track of it all because they got mixed up with their M1s and M2s and M3s. They sort of mingle in together. Very strange behavior. So the point is that by the time they get to Earth, only a third of them interact again as electron neutrinos. Now it sounds like science fiction, doesn't it? It sounds crazy. In the 1970s, the solar model, a standard solar model explaining what was going on in the sun was pretty well developed, and people really thought that they understood the processes that were powering the sun, including exactly how many neutrinos the sun should be producing. So this chap, Ray Davis, thought, well, why don't we try to measure the number of neutrinos coming from the sun? So in a mine in South Dakota in the States, he built a huge tank of chlorine, basically cleaning fluid, a huge tank of chlorine. And the idea is that when these neutrinos interact with the chlorine, once in a while, one of the neutrinos will hit a chlorine atom, and via this sort of inverse beta decay kind of process, it will turn it into an argon atom. So you've got this massive, massive tank there, and every once in a while, a chlorine atom turns into an argon atom. And what, there's Ray Davis in the picture swimming in the pool of water around, in the mine. What he did was that every few months, he would purge that whole tank, run the whole tank of chlorine through filters to count the very few argon atoms that were being produced by these solar neutrinos. And he counted them and only saw a third as many as expected. And people said, well, you're wrong, you know, you counting atoms in that massive tank of chlorine, you're joking, you know, it'll be a calibration error or something. He repeated the experiment over and over again and kept on for many years, decades even, came up with the same answer. And ultimately, in the end, nobody could really explain it. Either something was wrong with the solar model, or there was really some systematic that nobody could explain, or the neutrinos were oscillating. And indeed, for this work, once it was proven that the neutrinos were oscillating, Ray Davis received the Nobel Prize in 2002. I'll tell you what convinced me personally of the neutrino oscillations. That's the Super-Kamiokande experiment. This rather busy looking slide shows the Super-Kamiokande detector buried a kilometer underground in the mountains in Japan, in a mine in Japan there. And here's this picture of it again. This is with the detector mostly empty. It's a massive, massive tank of very pure water. As I said, I think 50,000 cubic meters, if memory serves. Is being serviced in this picture. So the guy's floating around in a boat, checking out the photomultiply tubes. They are electronic eyes, which are kind of close to the size of a football, I guess, and cost about £1,500 each. So many, many, many of them. The idea was the neutrino comes in, it will hit, I'll come to that in just a moment. So it's looking for atmospheric neutrinos. So a reminder that you get high energy cosmic rays coming into the atmosphere, producing these cascades of particles. And in this case, you get pions coming out, and the pion will decay to muon and a muon neutrino. The muon decays to electron, electron neutrino, and a muon neutrino as well. Actually, it's a muon anti-neutrino there, and that one's anti-neutrino, but never mind that. The point is that some of these neutrinos will go through the experiment, go through neutrino detectors that are sitting underground. There's another nice picture of Super-Kamiokande. Now, what happens when it does, if it's a muon neutrino, it hits the nucleus and a muon comes out and a sort of splash of other messy stuff. If it's an electron type neutrino, then an electron comes out and various stuff. How would these electric eyes see that? Well, what happens is what they see is essentially this muon and the electron. They give off what we call Cherenkov radiation. Now here you can see the sort of cylinder of electric eyes unwrapped to give that horizontal block in the middle and the lid and the base of the cylinder at top and bottom. And this is an example of a muon that's gone through. And you get a very, very sharp, well-defined ring out. And so you can look at that and you say, ah, yes, that was a muon neutrino coming from this direction. The electron neutrinos give much fuzzier rings, and so you can distinguish between them. And what Super-Kamiokande did, it looked at the neutrinos coming from above versus it counted them and counted the neutrinos that were coming from underneath, because they were made in the atmosphere at the bottom of the Earth and had come all the way through the Earth and hit the detector from below. And you see a graph on the right. The line in blue is the number that you would expect to see if neutrinos didn't do this strange business of changing from one kind into another. The line in red, sorry, the red data points are what you would expect to see if the neutrinos do oscillate. And on the left of the graph are all the ones that are coming all the way through the Earth from underneath. On the right are the ones that have come from above. And as you see, the further it goes through the Earth, the greater the probability that the neutrino has changed into a different kind of neutrino. So you see fewer and fewer of the muon neutrinos that were produced in the atmosphere. So that, to me, that was pretty convincing. Half of the muon neutrinos disappear while traveling through the Earth. Now, yeah. It was really, the whole business was really put to bed by this SNOW experiment. This is the Sudbury Neutrino Observatory, which is located in Northern Ontario, Canada. Beautiful, beautiful spot in the wilderness there, as you see. Lovely, amazing wildlife, bears, mooses, wolves, lots of mosquitoes in the summer, lots and lots of snow in the winter, and beautiful northern lights. Wild and dramatic place. And up there in Sudbury is a nickel mine. And that nickel mine goes some 2 kilometers underground. And there is a cavern excavated right at the bottom explicitly for the Sudbury Neutrino Observatory. And it looks like this. This is this ball 12 meters across. And they borrowed essentially Canada's entire supply of heavy water, put it in this detector 2 kilometers underground. Heavy water is great for this purpose because electron neutrinos can interact differently from other types of neutrinos in the heavy water. And what they saw, so it detects solar neutrinos in different ways. One way just counts the number of electron type neutrinos. Remember, in the sun, these neutrinos coming out they all started off as electron neutrinos because they were electron interactions. Another way of counting them counts any kind of neutrino. It doesn't care whether it's electron or muon or tau. So they've got these two different ways of counting. One only looks at electron neutrinos, the other counts all three. And what they found was that the number of electron neutrinos coming from the sun was only a third of the total number. So that really nails it. That absolutely proved that the electron neutrinos produced in the sun are actually turning into muon and tau neutrinos along the way. So neutrinos really do exhibit this extraordinary behavior of changing from one kind to another. And for this, the pioneers of those two projects were awarded the Nobel Prize in Physics in 2015. Kajita and McDonald. So it would be nice to investigate these neutrino oscillations a little bit more detail. They tell us, if you make the careful measurement of neutrino oscillations, they tell us, they don't tell us how massive the neutrinos are, but what they do is tell us the differences in mass, so M1 minus M2, etc. And they also tell us how well they mix with each other. So what fractions are, how much M1 and M2 is in an electron neutrino and so on. Now you can't go and put a detector right in the sun or in the upper atmosphere very directly, very easily. So what we do instead is we build accelerator experiments where we can put the detector at both ends of the journey. And also you can use you can use a lot more neutrinos and so make very precise measurements. And also incidentally look at differences between neutrinos and antineutrinos. So this is the MINOS project, the main injector neutrino oscillation search. As I mentioned, this is one that I was involved in. And the idea was from this accelerator near Chicago in Illinois, its Fermilab, you would shoot neutrinos a few degrees down into the ground, and they would travel along 735 kilometers through the ground, because remember, they're happy to go through Earth without interacting. And where they come out, we put in 5,400 ton detector. So we could study the neutrinos at the start of the journey and at the end of the journey and see how they changed en route. The detectors themselves look like this. It's like a loaf of bread with slices of steel plates to provide the mass, lots of target atoms for the neutrons to interact with, and then planes of plastic strips that actually detect, catch the light from charged particles. And so I won't go into a lot of details here, but the scintillators basically give off light when electrically charged particles pass through them. And you have one plane one way, the other plane the other way, like an XY grid. So you can see where your neutrinos go. And then we put a magnetic field on it as well. And this whole detector was situated half a mile underground. This business of underground detectors, by the way, this shields you from all the cosmic rays that would otherwise provide a lot of noise on the surface. And yeah, here you go. It's a disused iron mine that is now a state park that you can go and visit, see what it was like for the miners underground. This is the lift cage that we went down in. And actually, the whole detector went down in that lift cage, a strip at a time, and had to be built underground. Here it is. This is it half built, 282 planes. And this is a little bit about the near detector. It's on prairie land just outside Chicago. And yeah, here you see what we call an event display, a display showing what the detector shows of a muon neutrino that's actually come up from underneath. So it's come all the way up through the Earth. This particular one happened to hit a nucleus in the detector and made a spray of particles, and there was a muon track that went. And you can tell by the timing which event happened, which channels were triggered in what order, so you can see that it was going upwards, not downwards. And by the way, just for numbers, we would aim something like 10 to the 20th neutrinos per year at this detector, and out of that we would see about maybe 300 in a year. So what's going on? My screen doesn't want to, oh, here we go. It's going slow. Okay. So a successor to the MINOS project, which finished some years ago, is the NOVA experiment. And this is much, much larger. The FAR detector here is 14,000 tons. And it is all this active plastic scintillator. So again, with these little photomultiplier, well, actually avalanche photodiodes, it's not photomultiplier tube, not quite the same, to catch light from the scintillator. But it is a huge project. Here you see it in its natural state in its forest, the size, the scale of the FAR detector. And here, look, here it is end on. I mean, this thing is cathedral size. It's huge. And you see the collaboration of physicists and engineers in front of it when the very first that's the installation of the first plane. And if anybody wants to chase it up afterwards, there's a link to a time-lapse video to show some of the building. And I'd just like to show you again this event display to show you this is a muon in the nova detector, and you can see this very, very, very long track. Muons sort of last a long time. They're very penetrating. They go a long way. And looking at that, you know that's a muon, whereas in comparison, this is an electron. So this was an electron neutrino interacting, and it produced an electron and associated sort of spray of bits and pieces, but no long tracks. So you can really tell the difference between electron neutrinos and muon neutrinos. And jumping on the bandwagon, the Japanese used their accelerator on the east coast of Japan to send a beam of neutrinos the 300 kilometers underground to that same Super-Kamiokande detector that we saw earlier. And that's the T2K project. You don't have to go hundreds and hundreds and hundreds of kilometers to explore usefully explore properties of neutrino. This is the Bougie reactor that I mentioned earlier, and there are neutrino detectors close by that, looking for disappearance of anti-electron neutrinos. So seeing whether neutrinos, these electron neutrinos at low energy, whether they will oscillate very quickly. So investigating them as well. Same kind of principle. You have a detector with lots of shielding to protect you from particles coming in from the outside. So basically only neutrinos can get in undetected. They go into this sensitive volume in the middle. Very rarely, once in a while, one will hit a proton, and this same inverse neutron decay, you get the positron coming out, and you can detect it and identify it. So I think you get the idea of a lot of common themes in the way these detectors are working. And there's one in China as well that produced some interesting results about electron antineutrino disappearance. So this one actually is important, as it says, for sensitivity to differences between neutrinos and antineutrinos, of which more in a moment. One more neutrino detector. This one's really exotic. This sits right at the South Pole. This is the ice cube experiment. It turns out that ice at the ice pole is very, very pure, and there's a huge weight of ice which squeezes out bubbles and impurities. And so light from flashes after neutrino interactions can travel a long, long way in this very pure ice. So what they did, so you see on the left, you get some sort of astronomical event. And within the ice, there are these long, long, long chains of detectors, photomultiplier tubes that can catch flashes from neutrino events in the far universe, high energy neutrino events in the far universe. So that's going on right at the, as I say, right at the South Pole, which is pretty cool. So there are two big questions that are really the holy grail of neutrino physics at the moment. First, is the neutrino its own antiparticle? And second, perhaps related to that, this question that I alluded to earlier, why the universe contains so much matter, but almost no antimatter. As I said, that's really been a huge mystery in cosmology since the 1960s. Sakharov's famous paper on CP violation in 1964 really brought that question to light. Now, let's look at the first of these. Is the neutrino its own antiparticle? What is an antiparticle? You've heard of antimatter from science fiction, but it's real. There really is antimatter in the universe. And all particle types have got antiparticles. The properties are similar. They've got exactly the same mass, we believe. But electrical charges are opposite. So for example, the anti-electron is what we call a positron, and it's used in medical imaging, positron emission tomography, for example. Now, a neutrino, it turns out as a neutrino travels along, it spins, at least it has angular momentum. So the classical analogy is it spinning as it's traveling along. And you can imagine it spiraling along like a corkscrew, but it is what we call left-handed. So I don't know, am I on the screen? Can you see me or not? Maybe you can't. I don't know whether you can see me or not. I'm holding up my hand. But if you hold up your left hand in a fist, but stick your thumb out, imagine your thumb going in the direction of that arrow, then your fingers are curling around in the way that the spiral goes. And that's what we call left-handed angular momentum, spinning in that direction. So all neutrinos, in every interaction we've seen, all of the neutrinos have been left-handed. As far as we can tell, there are no right-handed neutrinos. They don't spin the other way. So only spin one way. Neutrinos are left-handed, but there is a certain symmetry in the situation, because although all the neutrinos are left-handed, the antineutrinos are right-handed. Now, big question is this the only difference? Is the neutrino really its own antiparticle, but just spinning the other way? So there's a process called neutrinoless double beta decay, where you get radioactive decay that emits 2 electrons, but no neutrinos. Perhaps it's only possible in this situation if the neutrino is its own antiparticle. So curiously, to investigate this particular property of neutrinos, people are looking very, very hard for a kind of radioactive decay where no neutrino is emitted, ironically. So that is, and this is what they've done. They've resurrected this SNO, Sudbury Neutrino Observatory, to an experiment that they call SNO Plus, and they put in, oh, I've forgotten exactly which element it is now, but an isotope that possibly could decay, undergo radioactive decay in this way, and so they are looking very hard for this neutrinoless double beta decay to see whether the neutrino is its own antiparticle. The other big question I mentioned is the question of why the universe contains lots of matter but almost no antimatter. Big Bang created them in equal parts. They all annihilated, and that mutual annihilation is the origin of the 3 Kelvin cosmic background radiation that you may be familiar with. But somehow, after all that annihilation, just a little bit of matter, 1 part per billion, was left over, and that little bit of matter is all of us. The sun, the moon, the stars, the planets, the galaxies, everything is that 1 part per billion that was left over after this massive cosmic annihilation. We don't really understand it. There's some law of nature that must treat antimatter a little bit differently to matter, to let there be a bit left over. In our accelerator experiments, we've seen tiny evidence of it, but not enough to explain the amount of matter we see in the universe. So the question is it possible that this asymmetry between matter and antimatter in the universe might be related to an asymmetry between neutrinos and antineutrinos? And the neutrino-antineutrino symmetry question, actually colleagues at Sussex are really, really high up and involved in leadership of this project. This is the DUNE experiment, Deep Underground Neutrino experiment, that goes back to that home state mine, and neutrinos will be shot from Fermilab. So they're reusing these facilities, you see, and this time the distance will be 1,300 kilometers through the Earth to this massive detector, billion-dollar effort that's going on in the home state mine. You see here, this is a simulation of what an event will look like when a neutrino hits and produces this little splash. And on the bottom right is the accelerator. So you accelerate your particles, you get a very, very focused particle beam. And in this long tube here, the pions that are made will decay and produce neutrinos, and they just go on in the same direction and go on through the Earth. Let's come to the conclusion then. Neutrinos are elusive particles, to put it mildly. Together, they've got more or less as much mass as the rest of the ordinary matter in the universe combined, but they hardly interact, and so they're very, very hard to detect. They can be used to probe properties of the sun, perhaps the center of the Earth, the cores of exploding stars. So really valuable and useful tools for these investigations. There are three types of neutrinos, three ways that neutrinos interact as electron neutrinos, muon neutrinos, and tau neutrinos, but they mix and change flavors. They sort of mingle and mix with one another. Neutrino detectors are massive, and they have to be just because neutrinos interact so little. So you need lots and lots of target to have a chance of catching them. Experiments with accelerators and reactors give us precise measurements of how these neutrinos mix with each other. And neutrinos may be their own antiparticles. Determining this question is an important goal for neutrino physics. Finally, the differences in behavior between the neutrinos and antineutrinos may help to explain the dominance of matter over antimatter in the universe. There's this little cartoon I love from Sid Harris, quarks, neutrinos, mesons, all those damn particles you can't see. That's what drove me to drink, but now I can see them. Thank you very much. A few credits at the end. I'll stop sharing the screen, and I'll be happy to answer any questions. If anybody's still awake at the end of that, I'll be happy to answer any questions you might have.
Philip, many thanks. I'm gobsmacked. I had some idea. I understood neutrinos. I have now a clear idea. I do not.
Oh, I'm sorry.
No, but that's because you've made it quite clear that there are all sorts of interesting questions yet to be answered. Do others have questions?
I'm interested, by the way, in feedback on this. So, but it doesn't. I don't need the compliments. But if people think I need to make bits clearer or whatever, if it's too technical, I'll be happy to hear that as well. So, just let me know. Anyway, sorry. Other questions?
I looked up on Wikipedia, and I think it's linear alkyl benzene, which is used in Snow Plus, according to Wikipedia.
Yeah, so that may be the molecule, but at the core of that, one of the atoms, one of the isotopes of one of the atoms,
right?
Has a tendency to this particular. Has a possible. There are only about 8, I think, where it's energetically possible for this double beta decay to go on.
Presumably, there's quite a lot of carbon in that.
There probably is. Yes. It's extraordinary, that whole effort in snow. It's the cleanest environment in the world in terms of clearing out radioactive background. They had to filter in the original snow experiment, the water had to be so pure that it was something like a factor of 1 in 10 to the 15, clearing out of radioactive isotopes. Just astonishing.
Other questions?
Yes, in one of the early slides, you showed a reaction diagram. And it was very early.
Yeah, the neutron decay probably.
It had a neutrino on one side.
Yeah.
And a proton. And then a neutron and I think an electron.
That was neutron decay. Let me go back to that. I did most of my career actually was spent studying neutrons, looking for a tiny asymmetry related to the question of why the universe is dominated by matter rather than antimatter.
It was an earlier one than that.
Oh, an earlier one than that. Okay.
Yeah, it was just a reaction formula.
No, it can't have been earlier than that. That was the beginning.
Right, okay then.
Oh, the inverse neutron decay, the one with the Reines and Cowan. This one here, yeah?
This one, yes. The mass look less than the mass and energy on the right.
Yeah, but the antineutrino coming in on the left has got enough energy because it's come out of the nuclear reactor. It's come from the decay it's come from a fission reaction in that nuclear reactor. That on the left, the antineutrino nu E with a bar on top, that's electron antineutrino. That's got quite a high energy, high enough energy to let this reaction take place.
So the neutrino on the left,
yeah,
is this neutrino has this tiny fraction of the mass,
yeah,
and energy or combination of the electron. So the extra mass and energy is coming from its speed. Is that right?
Yes, yeah. So a photon, a particle of light, if you like, that's got no mass at all, but it can have plenty of energy, like a gamma ray.
Yeah.
Has lots and lots of energy, but no mass. And in fact, they used to think the neutrinos were massless. So it can carry energy, that's no problem. And as you say, that's associated with its speed, which is very, very close to the speed of light.
Okay. So that's why it produces that's why it produces more mass and energy on the right-hand side.
Yeah, yes, there's enough energy there to produce the neutron and the positron and have a little bit left over for the neutron and positron to wander off with a bit of kinetic energy.
Okay. So there are no neutrons that deviate from this and are really almost as heavy or even heavier than an electron, or even close to it.
So I'm not quite sure that I understand the question, but I may be able to answer specifically this reaction you catch because the positron on the right, the E plus on the right, that's an anti-electron, and it will relatively quickly, it will hit an electron in the scintillator, and the two of them will mutually annihilate, and they'll produce two gamma rays, two photons, and those two gamma rays will go off in opposite directions. And because it is electron and anti-electron, you know the energy very, very precisely. And so you see a sort of signature of two gamma rays with exactly the energy you expect, and you know it's come from there. I think there's also a little something, the neutron may be captured after some characteristic delay or something, but I don't quite remember the detail of that. Anyway, the signature of the reaction is quite distinctive, and they found it. So,
okay.
I'll stop the sharing now, so in case anybody else wants to ask.
Any other questions? No? Well, Philip, thank you very much indeed for giving your time and entertaining us. That was stunning. And it's one of these things where I think the questions will occur to one tomorrow, or
That's
worse.
Fine. That's fine. Let me know.
even worse at 3:30 tomorrow morning.
Okay, thanks very much indeed. It's a lot of fun.
Good, thank you. Well, thank you to all of you who've participated in this AGM. It's always particularly grateful to Philip, because it's quite hard to make an AGM more fun than just an annual general meeting. And this, I think, has made it well worthwhile. Just a little thought. Gas is your society. To make it work and for us to rebuild it to not just what it was before COVID, but to what we would like it to be, it needs all of your efforts and all of your contributions. So please feel free to offer to volunteer in some way, or suggestions, and by all means email me. with whatever takes your fancy. Thank you for your time.
Thank you. Bye-bye.
Thank you.